So we like to begin a new unit. Our last unit was about the algebra of matrices and about determinants. Those two topics went together pretty well. We want to start with our final unit, which is going to be about vector spaces and subspaces. And then we're going to look at what are called eigenvectors and eigenvalues. So the first big part of our unit is about vector spaces and subspaces. We've talked a little bit about vector spaces when we introduced Rn. Vectors in Rn, we said that essentially the vectors in Rn form a vector space. So we've been through these properties before, or these axioms I can call them. So what is a vector space, or a real vector space? Yeah, so let's talk about a real vector space. So a real vector space, it's a non-empty set, let's call it V, of elements, and the elements are called vectors. And this non-empty set of vectors is equipped with two operations. One is a vector addition operation, and the other one is called a scalar multiplication operation. And these satisfy, these operations satisfy 10 axioms. So what are the 10 axioms? For every three vectors, u, v, and w, and for every pair of scalars, r and s, number one, if I take two vectors, u and v, and add them together, they end up back in the set of vectors. So basically a vector plus a vector is a vector. Property two, if I take u plus v, that's the same thing as v plus u. So vector addition is commutative. Vector addition is commutative. The third property, if I take three vectors, u plus v, and then plus w, that's the same as taking u and then plus v plus w. So we say here that the addition operation between vectors is associative. The fourth property is that there's some zero element, we call that the zero vector, that when you add it to another vector, you get back the original vector. This is called the additive identity. The zero vector is an additive identity. The fifth property is that for every vector u, you can find an element opposite of u, or you call it the additive inverse of u, in the vector space. So there's a negative u in the vector space that when you add it to the u vector, you get the zero vector. This is called an additive inverse property for vectors. The sixth property is if I take a scalar r times any vector, the resultant vector is in the vector space. Yeah, so a scalar times a vector is always a vector. Seventh property, if I take r times two vectors added together, it's the same thing as r times u plus r times v. This is said to be a distributive property. This is scalars distribute over vector addition. Scalar multiplication distributes over vector addition. Property 8, if I take two scalars and add them together, and then multiply that by a vector, that's the same thing as the scalar r times u plus the scalar s times u. And it looks like we have a little mistake here. Let's fix this. It should be an equal sign right there. So here we say that vectors distribute over scalars added. So vectors distribute over two scalars added. Property 9, there's kind of an associative property here for scalar multiplication. So r times su is the same thing as r times s times vector u. And finally, the one element, the number 1 times any vector, is back to that vector. Yep. All right, so these are the 10 properties, or 10 axioms for some set V to be a vector space. So we already said way back at the very beginning of the semester, probably the second or third week, that Rn is a very well-known vector space, and that's the one that we've dealt with primarily, and that's the one that we're primarily going to deal with. We're not going to really do a whole lot with any others. Let's write down some examples here of vector spaces, of real vector spaces. Vector spaces. Now, why do we call them real vector spaces? It's because our scalars are real numbers. You could actually talk about complex vector spaces if you have complex numbers being your scalars, but we're only going to focus on real vector spaces where our scalars are real numbers and our entries in our vectors are real numbers. So number one, a real vector space, let's call it VRN, right? This is the one we've dealt with all semester long. Rn, and a typical representative of Rn would look like this. A vector A, right? It would have elements or entries A1, A2, and so on and so forth. AN, right? That's what a typical vector would look like in Rn. All right, let's do another example. V, another vector space, R adjoin X. R adjoin X. These are polynomials. So a typical vector we would write as P of X. Now really you're supposed to use a capital X when you're doing polynomials in this way. You would say, so a typical polynomial looks like a sub 0 plus a sub 1 capital X plus a sub 2 capital X squared, and so on and so forth, dot, 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 a sub n capital X to the n power. So this is what a typical polynomial looks like. And the x's are your variable. It's an unknown, and the a0, a1, a2, an, those are actually going to be numbers. Those will be real numbers, those coefficients. Yeah, so basically if you were to add two polynomials, you get a polynomial, and it would satisfy all those 10 properties. So the set of polynomials forms a vector space. Number 3, now here's another vector space. C, A comma B. These are the continuous functions. The continuous functions defined on the interval AB. So a typical characteristic or a typical representative of this vector space would be f of x is a continuous function, right? A typical continuous function is a continuous function. So most of the functions that you're familiar with, that you deal with in calculus, are continuous functions. In fact, they're usually differentiable functions. Yeah, so a continuous function would be like e to the x, right? That's actually differentiable. X squared plus 5x plus 3. Polynomials are continuous. Yeah, so continuous functions over intervals. They actually form a vector space. If you take two continuous functions and add them, it's going to be continuous. And all those 10 properties, you can satisfy all of those 10 properties with the set of continuous functions on a closed interval. Here's another one, number 4. This is something that you might deal with if you get into a more advanced linear algebra class or functional analysis. L2, A comma B. So these are called the square integrable functions. So functions that you square and you can take the integral of. So a typical function would be like f of x is a function where you can take the following integral from a to b, absolute value of f of x squared dx exists. So that integral exists. So you actually could take that integral. Yeah, so any function where that squared, when you square the function and then integrate, and you're able to do that integration, that's called a square integrable function. So square integrable functions, they form a vector space. You can add square integrable functions together and you get another square integrable function. All the other properties, axioms are satisfied, all 10. Here's another famous one, another famous vector space that you might encounter in a more advanced linear algebra or something called functional analysis class. V equals lowercase l, kind of a script L squared. So these are called your square summable sequences. Just L2, square summable sequences. So a typical example of this is going to be a sequence, A sub n. So A sub n is a sequence that's square summable. what does square summable mean? It means you take the sequence, an quantity squared, and you look at the series of that, the associated series, converges. So if the series an squared converges, then an is called a square summable sequence. Yeah. So if you were to take two square summable sequences, add them together, you get another square summable sequence, and all the 9 other properties. So the 10 total properties would be satisfied. So these are just some examples of some common vector spaces that show up in linear algebra and more advanced classes that look at vector spaces. But primarily we're just going to deal with Rn, that's the common one, right? Vectors with entries, first entry, second entry, up to an nth entry. They're simple to deal with. Okay, so that's the abstract definition of a vector space. We want to move on. What is a subspace? A subspace. Here's another definition. What is a subspace? A subspace of a real vector space, V of a real vector space, is a non-empty set non-empty subset, I should say, subset. Let's call it H of V, non-empty subset H of V, that is itself a vector space. That is itself a vector space. So I'm going to draw a little picture diagram. So let's say out here we have our vector space V, right? V is a set of objects that satisfies 10 different properties. And inside of V we have a subset called H. And H satisfies all the properties of a vector space. But H is potentially smaller than V, but it still satisfies all 10 properties of a vector space. So it's like a subspace. A subspace is kind of a vector space within a vector space. So formally, that's what a subspace is. Now, here's a really important theorem. We're not going to prove this one. This one is going to be called the subspace test. The subspace test. So how do you test if a set of vectors is a subspace of a larger vector space? And that's the question. Now, most books give this as a definition for a subspace, but in actuality, we have given the correct definition here, that a subspace is just a vector space within a vector space. So most books give this theorem as a definition. It's really not a definition. It's actually a theorem. So your book here, the book we're using, David Lay's book, gives this as a definition, but we're going to state it as a theorem. We're not going to prove this theorem. Suppose H is a subset of a vector space, V. Background information. H is a subspace of V if and only if the following happens. Number one, the zero vector, which is in V, is also in H. So the zero vector is an element of H. Number two, if I take two vectors, U plus V, and add them together, and those two vectors, let's say, are from H, then the sum should be in H as well. So what I'm saying is U plus V is in H for every pair of vectors, u and v and h. Yeah. So what we're saying here again is if I take any pair of vectors, u and v from h, and then I add those vectors together, it ends up in h. And finally, number 3, r times a vector u is in h for every vector u in h and every scalar r in the real numbers. Yeah, so what this one is saying is if I take a scalar, any scalar, times any vector u in h, then ru, the scalar times the vector, must be in h as well. So basically we have 3 properties that you need to satisfy in order for h to be a subspace of a real vector space. Now, if you actually wanted to prove this theorem, you'd have to say, okay, these properties alone, these 3 properties, from these 3 properties, I can prove all the other 10 properties of a vector space. I mean, you could sit around and do that. It takes a long time. It's not difficult, just very tedious, and we're not going to bother doing that. Just take my word for it. These 3 properties imply the other 10 properties, basically. Yeah. So let's do one quick example, maybe. One quick example. Let's show that this set of vectors H is a set of vectors of the form A0C, just like AOC, right? Such that A and C are real numbers. Yeah, that 0 is not showing up too well. Is a subspace of R3, is a subspace of R3. And we want to use the subspace test to do that. So, proof. Here we go. We're going to prove this. So the first thing you want to do when you're proving something is a subspace, you want to declare that your set H is a subset of R3, right? It has to be a subset. That's what we want to do first. So we're going to note that H is a subset. That's the symbol for subset. It looks like a sideways horseshoe with an equal sign underneath as a subset of R3. So why is H a subset of R3? Well, look at H, right? The elements of H have 3 entries, right? A, 0, and C. A, 0, and C. So, I mean, it's a subset, right? It's a subset of R3, H is. Okay. So, now what we have to do the first big step. We have to show that the 0 element is in here, right? 0 element. That is kind of the first step right here, right? The 0 element is in H. So, let's just say, observe that the vector 0, 0, 0 is an H. And we have to give a reason. We have to reason our way through it. So why is the vector 0, 0, 0 in H? Why is the vector 0, 0, 0 in H? Well, let's look at our form of elements for H, A, 0, C. So what we could do, we could set A equal to 0, right? And set C equal to 0, and then you just have 0, 0, 0. So that would definitely show up in H. So I'm going to say, observe that 0, 0, 0, that vector, the 0 vector is in H, since it satisfies, that vector satisfies the form A0C by setting A and C both equal to 0, right? Just plug in A 0 for A and C, and you got the 0, 0, 0 vector. Okay. So the first big step is done. Let's see, can we do, well, before we do the second and the third step, you always want to set things up properly. Let me show you how to set things up. So what you're going to do, you're going to scroll, and you're going to say let, so we're not doing 2 and 3 yet, we're preparing for it, so we're going to say let U and V be vectors in H, and let R be a scalar, a real number. What does that mean about U? Let's think. What form is U going to take on? Well, we know that the first entry is present, right? And the third entry is present. The middle entry is going to be 0. So we're going to say then that means U is going to take on the form, let's say U1, 0, U3, right? That's the form of U, right? U1, 0, U3. And V, since V is an element of H, it's going to take on that same form. What form is that? Well, V is going to be equal to, it's going to have a first arbitrary entry, let's call it V1. Second entry is going to be 0. And the third entry is going to be arbitrary, let's call it V3. Okay, now we're ready to do the second step. The second step is to show that when I add two vectors together, they're in H, right? The sum of those two vectors is in H. So let's see. So this is step 2. And let's say note. So let's add our vectors together, U plus V. Let's add them together. What happens when we add U and V together? So for the first entry, we're going to have U1 plus V1. Our second entry is 0 plus 0, that's 0. And our third entry is U3 plus V3. All right, so we've added our two vectors. The question is this resultant vector, U1 plus V1, 0, U3 plus V3, in H? Well, yeah, right? H is just things of the form arbitrary entry, 0, and then an arbitrary entry. And that's what we have here, right? U1 plus V1 is an arbitrary entry. 0 is our middle entry, and our third entry is an arbitrary entry, UV plus V3. So this is an element of H. And let's do a step, final step. Do this in yellow, maybe. And step 3, what do we have to do for step 3? So you have to just show that if I take a scalar here and multiply it by any vector U, that it ends up in H, the resultant vector. So here, I'm going to take R times a vector U, arbitrary vector U, and that's going to be what? Okay, so look at vector U, right? U was U1, 0, U3. So when you scale that by R, you're going to have what? RU1. R times 0 is going to be 0, and then RU3 will be your third entry. So the question is RU, is this resultant vector in H? And it is, right? It's an element of H. Right, H took on the form an arbitrary entry in the first place, 0 in the second place, and an arbitrary entry in the third place. And that's exactly what we have. So this is an element of H. So what we can do now, since we've satisfied all the 3 criteria, right? There are 3 criteria. We're just going to say therefore, H is a subspace of R3, the vector space R3. And that's exactly how you would prove that a set is a subspace of a vector space using the subspace test. The subspace test.